Okay, so it's my pleasure to introduce Omar León Sánchez from the University of Manchester, who'll speak on differentially large fields and PAC differential fields.
All right, thank you very much, Dave. And first of all, of course, thank you very much for to the organizers for inviting me, giving me the opportunity to talk about this here. And just thank you for the organization, not just the workshop, but the program and all the activities. Right. So today I want to talk about some results with Marcus Stressel about differential large fields. And this part of the talk, part one, I think some people might have seen this in some logic seminars, but please bear with me until the second half of the talk when I want to talk about some results with Daniel Hoffman about PAC differential fields. Okay, so it's two parts. So part one. Part one will give an introduction to what are these this new class of differential fields, namely differentially large fields. And I'm going to pay special attention to the field of Laurent series over K. It really plays an important role when talking about differentially large fields. And the motivation, of course, comes from the algebraic notion of large fields and the application. I will touch a little bit on this in a few minutes. Okay, this is the aims for the first part of the talk, which, as I said, some people in the audience might have seen this before. Now, the second part is I'm going to give a quick review of what's it mean for a differential field to be PAC differential. Or sometimes we also call this pseudo differentially closed, and how it relates to differential largeness. And then I will talk about kind of a general setup that produces PAC differential fields in the context of finite groups acting on differential fields. Okay. And at the end, I'll just make an observation that kind of in parallel to the results about bounded PAC fields that are well known, the theory of a bounded PAC field is simple and other properties. It's more of some observations around this. Okay, these are the aims for the next 45, 50 minutes. Okay. Of course, there's any questions. Well, I don't know if there's any rules, but I'm happy to answer questions, whether it's in the chat or you can just speak up at any point in the talk. Okay. Right. So quick preliminaries and conventions. During this talk, I'm assuming that all the fields that appear are of characteristic 0. Okay. It's because in the differential setup, this is a very convenient assumption. Okay. And a reminder of a basic model theoretic definition that existentially closed. What does that mean? Recall if I have two structures in a given language, one is a substructure of the other, we say that the bottom substructure is existentially closed in N, the top substructure. If for every quantifier-free formula with parameters in M, we have that. If there exists a realization in N, the top one, then there must exist a realization in the bottom one. Okay, just to remind you what it is in case it's not at the top of your mind. Okay, all right. I think that's it. That's the preliminaries. Okay, so before talking about what differentiate large fields, what are large fields in the algebraic context? So a large field is a field with the following property. A field K is large if for every algebraic curve over K, if that curve has smooth K rational point, then the curve must have infinitely many K rational points. Okay. Now, there's many characterizations of being large, several ones. Okay, but there is one that I'm really interested in today, and it's the following one. A field is large if and only if it is existentially closed as a field in its Laurent series field K double bracket T. Okay, as fields, of course. This is just at the field level. Okay, and this is the definition that I want to focus today. Okay, especially when I move into the differential context. Okay, so just to stress out, a field is large if and only if the field is existentially closed in the field of Laurent series. Okay. Okay. Questions, comments?
Can you say something maybe about conceptually? Is there an explanation for why these should be equivalent?
Yes. So if you remember, when you look at smooth points in a, say you take any algebraic variety, right? When you look at smooth points, you're really sort of looking at completions, if you like, of somehow your coordinate ring. And that somehow corresponds to looking at the completion of, say, the polynomial ring. You're looking at the Laurent series field, right? And so if you find a smooth point, that means that you can actually find a point in your variety in the the completion in the Laurent series field. And then the fact that you can find infinitely many of them tells you that you are sort of existentially close in the coordinate ring of your variety, and then you can bring it down to K. So that's kind of the idea, that the Laurent series field are completions of the polynomial ring.
Thank you.
I guess that's sort of, hopefully that makes sense. Right. All right, now examples of large fields, right? Algebraically closed fields, but more generally, pseudo-algebraically closed fields. I will remember the definition of the latter one later. Real closed fields, pseudo-real closed fields, p-adically closed fields. I'm taking rank 1 for now. That's fine. Pseudo p-adically closed fields, and also, in fact, Laurent series fields are always large for any field K. And this follows from the last one, that any quotient field of a local Henselian domain is large. Okay, so really, if you have a non-trivial Henselian valuation, you will be large. So, okay, generally, if you take the quotient field of a local Henselian domain, you're going to be large. So these are all examples of large fields. So it's a big class. It's really, really a big class. Okay, with interesting properties, as I'll mention in the next slide. But of course, now you wonder, we have our non-examples. There's also lots of non-examples. And then basic ones are the rational numbers. They're not large. And also any algebraic function field will also not be large. You can see this because, kind of, if you wanted more Delvey kind of results give you why these are not large. Okay, this is non-examples. Okay, now so large fields, they sort of have a nice field arithmetic connected to them, and there are many results, many results around large fields. The one that I find really fascinating is that the following version of the Galois inverse problem is completely solved over large fields. So if you take a large field K, and you take a finite group G, arbitrary finite group G, then G is the automorphism group of some Galois extension of KT. Okay? So any finite group can be witnessed as the Galois group of some Galois extension of KT over a large field. I think this result was known for algebraic closed fields since 60s or 70s, but in the 90s, Florian Popp proved that can replace algebraically closed for large fields. Okay. Anyways, there are also many other applications to field arithmetic, but the ones that I want to pay attention to today are the following 4. First of all, the class of large fields is an elementary class. You can axiomatize it in first order logic. The second one is that the existential theory of all large fields is just existential theory of Laurent series fields over Q. So every system of polynomial equations with no parameters, so over Q, right? If it's consistent within large fields, then if and only if it's consistent in Q double bracket T. Okay. The other one is that algebraic extension for large fields are again large. Okay. And the last one, which will be important for us, is that PAC fields are also large. Every PAC field gives you. This I already mentioned examples. Okay. Okay. This is just a quick reminder of what large means in the category of fields. Now, the motivation for us is there a suitable analog for large in the context of differential fields? What sort of suitable means? Well, it's one that has kind of parallel properties. What is that? What are parallel properties? Okay, I'm not going to be very precise about this, but kind of one could say is that one definition that would play a similar role within differential field arithmetic. So in particular, within differential Galois theory. Okay, but this is kind of the motivation. Okay, I'm not being very precise about this. This is our motivation. Now, I also want to say something about clarity. Clarity means that all of the results that I'm going to state today, except for one, they hold for if I work in the context of several commuting derivations. But for clarity of exposition, I'm going to focus in the case of just one derivation. Okay, I think some people will feel more comfortable working with one derivation, but as I said, all but one just hold in several derivations, commuting. And if you can actually last through the whole talk, and you can tell me at the end, oh, this is the one that doesn't hold in the several commuting derivations, then yeah, it's kind of a challenge for everyone at the end of the talk. Okay. And if you can't figure it out, you can just ask me and I'll be happy to tell you which one is it. Okay, fine. Any questions? Okay. So I think let's just get to it. I think that, yeah, the next slide, let's get to it. What is our potential or proposed definition of a differential large field? It's the following. A differential field, K delta, remember one derivation, characteristic 0, remember, is differentially large if the underlying field is large and for every differential field extension, the following holds. If K is extensionally closed in L as fields, then it must be so as differential fields. Okay? So this is our proposed definition. And of course, you can ask, why do we think this is the right definition? Well, it turns out that we can give a characterization of this. And we can characterize this by saying that differentially large fields are characterized in terms of being existentially closed in León series. So again, let me remind you that a characterization of field largeness was that you were existentially closed in León series. So here, in the next couple of slides, I'm going to state the differential analog of that. Okay, but this is the definition. Definition is that the underlying field is large, and if you're existentially close at the level of fields, then you must be existentially close at the level of differential fields. Okay. So, okay, we're moving towards giving this other characterization of differential largeness. So I need to talk about the León series field. What sort of derivations do we want to have on it, right? We need to talk about some sort of derivation on the León series field if we want to have a characterization of differential largeness within the León series field. Okay, so what are the possible derivations in K double bracket T, extending the one on K? Remember, K delta is a differential field, and I want extended derivation to the León series field. Well, there's many. There's a lot. There's a lot of them. But there's a canonical choice, okay? And so there's this fact that one can prove that there is a unique derivation on the León series field with the following three properties. First of all, the derivation extends the one on K. Second, the derivation on T is 1. And third, that it commutes with infinite sums, meaning that exactly the quality that appears in the display there. Okay? So there's only one with these three properties, which are very natural properties. So from now on, whenever I have some León series field and I say this differential field, I mean with respect to this derivation, this unique derivation partial. Okay, that's it. Okay, so what is the characterization? Well, it's exactly the natural one with respect to this partial. So recall a field is large if and only if it is existentially closed in K double bracket T. Well, we have this characterization for differential largeness, that a differential field is differentially large if and only if it's existentially closed in the Laurent series field with this equipped with this derivation partial. Okay. And this sort of indicates, or at least, yeah, it gives us some evidence, if you like, that this is potentially the right definition for the differential analog of largeness. Okay. So now for the rest of the, well, maybe the next 20 minutes, 20, 25 minutes, I just want to present some properties of differential large fields, okay? Which will resemble the properties of about large fields that I mentioned a few minutes ago. Okay. Again, if there's any questions, please feel free to ask. Right. So what's the first thing? Oh, sorry. Did I say right? So now consequences of this theorem. That's right. Consequences of this theorem. Right. Recall that the theory of differentially closed fields, or differentially closed fields, what are they? They're just existentially closed models, right, of theory of differential fields. Okay, so a corollary of the previous theorem is that we can characterize being differentially closed with the following two conditions. Okay, a differential field K delta is differentially closed if and only if the underlying field is algebraically closed, and the differential field K delta is existentially closed with the Laurent series field with respect to this derivation partial. It gives us also not only do we get a characterization of differential largeness, but it also gives us a characterization of being differentially closed using this sort of prototype differential field, if you like, K double bracket delta comma partial. Okay. And we get a similar characterization of this other class called closed order differential fields. So now for this one, we are in the context of ordered fields, or formally real fields, right, equipped with the derivation. And if you look at that class and you look at the existentially closed models, then those are the closed ordered differential fields. And you can also get a characterizations of those by saying that K delta is closed order differential field if and only if the underlying field is really closed field, and K delta is existentially closed in the Laurent series field.
Omar, I mean,
yes.
In the second point, are you working in language with the ordering? In the second point, or not?
No, I'm not.
No. But you could. But you could if you want.
Oh yeah. I could if I wanted to. But so let's just think of in number 2. Let's think just as formally real fields. So I'm not putting any order right now. So yes, no order. It's just at the level of the field language. Okay. Thank you, Anna. Any other questions? Okay, so just one thing to point out here is that in the second one, so if K is orderable, then K double bracket T is also orderable. So, I mean, you need this, right? Okay, so one is orderable, but I'm not using this. Okay. Okay, now a few minutes ago I said that the class of large fields was first order axiomatizable, right? Well, it turns out that the same is true for differential fields, that differentially large fields. The class of differentially large fields is also elementary. It's also first order axiomatizable. And here are some axioms. Here are some axioms. One can give several axioms, but I think these are the simplest ones. They're very clean, I think, in the spirit of Bloom axioms, if you like. So differential field is differentially large if and only if K is large as a field, that's first order. And for every pair of differential polynomials Fg, one having order less than the other, if, and this condition doesn't appear in Bloom axioms, but you need this in the large context, you need it. If the system F equals 0, G non-zero, and then this other one, which click here, this one is what is usually called the separant effect. Separant effect. Okay, the separand.
Yeah. What is this? Or what is this?
I'm sorry, what's the question?
So what is this? What is this step on?
What? Sorry, what is this?
Yes.
Okay, so you look at the polynomial f, differential polynomial f, and I'm assuming it has order m, right? So if I look at it as an ordinary polynomial, in algebraic polynomial, then you know it has variables x, delta 2x, all the way to delta mx, all the way to delta mx, right? This is the highest variable appearing on f.
Oh,
okay. Now I do.
Now to it.
Okay, perfect. And then I take the partial derivative, the formal partial derivative of that with respect to that variable. And this is usually called the separand. Anyways, thank you for the question. I think for maybe other people, this was also good to clarify what this means. Okay, so you have this system, f equals 0, g non-zero, separand non-zero. If that system has an algebraic solution in K, which by algebraic, I mean what I just said now, that any differential polynomial, right, you can look at it as an algebraic polynomial in several variables, where the algebraic variables are x, delta 2x, blah, blah, blah. But you look at them not as one differential variable, but as several algebraic variables. If you look at it that way, and you find an algebraic solution in K, then the condition is that you can find a differential solution. Okay, and that characterizes being differentially large. If I can find an algebraic solution of that system, then I can find a differential solution of the system at the bottom. Okay. Okay. So this is first order. One can write this in a first order way. So this axiomatizes differentially large fields. Okay. Good. First order axioms. Okay, so one could ask, okay, now we know that we have this characterization of differential largeness. We know that the class is first order, but how about examples? Can we give examples, like interesting examples? Okay, first of all, it's really not hard to see from definition that any differentially closed field is differentially large. Okay, really from the definition, not from the characterization, but from the definition. Also from the characterization, but from the definition is straightforward. Also from the definition, you get that closed order differential fields are differentially large. Okay, but okay, is there more? And yes, the answer is there's lots more. It follows from the following theorem. If you take an arbitrary differential field with underlying field being large, okay, that's the only condition here. You have a differential field and the underlying field is large, like your favorite large field. Then I can find a differential field extension, L delta, such that L delta is differentially large. And more importantly, this extension L at the level of fields is an elementary extension of K. Okay, you can start with, K could be your favorite large field, like maybe a p-adequate closed field or some, Henselian value field or something. And you can always build differential large fields with the same elementary theory as the one you started with. Okay, so this is also a way of constructing these differential large fields. But okay, at this point you could ask a very natural question is, okay, these are kind of existence theorems, right? You could okay, you can always build these things, but you can always say, okay, but what if I want to actually construct one explicitly? Like I want to more or less like see one, not just have some existence result, but actually see how can I build it, not with your own hands, but kind of with your own hands. And this is the next construction. Okay, so construction. If you take any arbitrary field, any field K, right, and then I take differential, any differential field K, and I take Laurent series field with the canonical derivation partial, then that's never going to be differentially large. That's something that might kind of throw you off a little bit, but it's not that far actually. It's not that far from being differentially large. It is not close, but it's not that far being differentially large. And this is the content of this theorem. Let's start with the differential field. your favorite differential field, okay? That's it, that's the only assumption, characteristic 0. Okay, and now do this construction. K0 is K, and then K1 is Laurent series field over K with the canonical derivation, and then K2 is Laurent series field of K1 over K1 with the canonical extension, right? And then continue. And then you get a chain, of differential fields, take the union of that chain, and we call this L. Then turns out that this union is already differentially large. You don't have to go, beyond that. This union is already differentially large. Okay? There's a way to actually construct differentially large fields, taking unions of this sequence of taking Laurent series fields. Okay, and then I just want to point out that you get something that I find it interesting, is that suppose that in this construction, instead of taking Laurent series field, you actually take something a bit bigger. You take Poisson series. Okay, you take Poisson series. You take some roots of things. You take Poisson series, and say you start with something which is algebraically closed. So you suppose that you started with a differential field K delta, and the underlying field K was actually algebraically closed. And then in this construction, you start taking Poisson series over K, the Poisson series over the previous one. And of course, each of these steps gives you something which is algebraically closed. But turns out that the resulting differential object is already DCF. It's already a differentially closed field. This gives you a way of constructing differentially closed fields using kind of natural field theoretic constructions. And then similarly for building closed order differential fields out of a real closed field. Okay, so you just use the fact that if I start with an RCF, then the Poisson series is also RCF. Okay. Okay, so now we have these explicit constructions of differential large fields, and also DCFs and CODFs.
Sorry.
Yes.
Just to be sure, this natural derivation that you get is sending Tn to 1 each at a time?
So yes, so you start with any differential field, right? In the Laurent series, the derivation of Laurent series, it maps T to 1, right? And then when you repeat the process, then you have to add another variable, right? So maybe the first variable you added was T1, just to say something, right? Okay, now T1 goes to 1. Now in the next iteration, you add another variable, maybe T2, right? And then this T2 goes to 1 as well. Does that answer the question?
Yes, but then the derivation means that they are just different by a constant.
Yes, yes, absolutely. Very, very good point. Very good question. This is something that we've been thinking about. Thank you for asking that. We have basically no control on how the constants grow on this iteration. Does that more or less answer the question?
Right.
Yes.
Okay.
Yes. So yes, this construction is quite suitable for our purposes, but unfortunately, every time you do it, as you pointed out, you're adding new constants. It would actually be interesting to say what sort of control do we get on the constants in this construction. Yes.
Thank you.
No problem. Any other questions?
So I guess that if you want to, to preserve constants, the constants should be somehow, existentially close in some sense, right? Because after adding, you need to, after adding this extra structure, then you can just take the reduct and see that the constants there should be, again, existentially closed in this bigger guy, right?
If the new field of constants remains existentially closed in the bigger guy, is that what do you mean?
Yes, but to get that, if you want to preserve the constants, you should already start with a field of constants, which is in some sense existentially closed, right? Rich in solutions.
Well, if you perform this construction with this canonical derivation, you're always going to add constants. So it's impossible to preserve the constants in K in this construction. So
I'm just thinking about any other option, right?
Right.
get
Right.
you know, extension which is large, but yeah.
Yes,
but
yes,
preserve
that's
the
right, that's right.
constants.
That's right. So we thought about this, absolutely. We thought about this. And of course, there, as I said, this derivation that we have is a canonical one, but it's not a unique. There's many choices. And so we try to modify it, right? And to try to have some control on the constants. For instance, if you map t to maybe t itself, right? Instead of mapping it to 1. But then you have problems, because then you don't really characterize differential largeness in terms of this one. So if you change the derivation to another one, you have to be careful that this new derivation still characterizes differential largeness, and that was a big problem that we couldn't figure out. So there might be some options to do, but it wasn't clear. But it's a very good question. Any other questions?
Actually, I was wondering, in the same ways that with differentially closed fields, you can have a differential closure which does not increase the constants. Maybe, you know, you could have an elementary substructure of this L, which does not increase the constants.
Yeah, that's a good point. That's right. That's right. Yeah, because just if you think about it, the differential in the DCF context, well, inside this construction, there will be a differential. If you're looking at it in the where you start with an ACF and say you actually use Poisson series and you do this construction, the construction increases constants, but inside of it, there's going to be a differential closure, and that will not change constants, right?
If you start with the reals, then you will have to introduce a constant because the constants will be dense, right?
Oh, yes, that's right.
And
yeah. So in the case of CODF, the picture
you will immediately have to introduce a constant.
That's right. That's right. Yeah. In the case of CODF, the picture is completely different to the DCF case in terms of constants.
But Omar, you know,
Yes.
In this very special case of finding PV extensions, which we
Yes.
did before, it's complicated, even in that case, to find a PV extension with no new constants. It's a bit complicated.
Yeah,
Even in
sure,
that case,
sure.
the situation is you can do it, but it's hard.
That's right. That's absolutely right. Yes, that's absolutely right. That's absolutely right. Yes. So even in that very special case, it is hard. You need some assumptions. Absolutely. Yeah. No, it's a very good question. I mean, kind of preserving constants is a very kind of desirable property, but under this construction, it's very subtle. Indeed. Okay. So I hope that more or less answered all the questions. Anything else? Maybe I saw something in the chat. One will have to start with essentially closed set of constants that can be suggested. Yes, so exactly. So for instance, Anand brought this up about building PV extensions. And so one natural assumption to get a PV extension, so something that doesn't have any constants, is that the constants are existentially closed in the field. That's right. So this is a natural assumption to kind of make this work. That's right. But still, even with that assumption, in the general differential large case, I think it's still complicated. Okay. Okay, thank you for the questions. So now, right. So the existential theory. So the existential theory of a structure, just to remind you, it's just a set of existential sentences, right? There exists something that quantifier free X, and the ones that are true in M. So that's the existential theory of a structure, the set of existential sentences that are true in M. And if you have a class of a structure, the existential theory of that, you just take the intersection, right? You take all the existential sentences that are true in all these structures. And in the case of large fields, you take the class of large fields, and you want to know which existential sentences are true in all large fields. Well, it turns out that those are the existential sentences that are true in Q double bracket T. Okay, so another way to say this is that you give me a system of polynomials. That system of polynomials, right, will be consistent within large fields, even only if you can find a solution in Qt, double bracket T. Okay, and then for differential large fields, it's very close, but it's not exactly. The theorem is that the existential theory of differential large fields is that of Q double bracket T1 and then double bracket T2. Okay, you need to actually go this iterated construction, you need to go to a second step. And then that works. If you look at the existential theory of that one, then that's the existential theory of all differential large fields. So if you want to check that a system of differential equation holds in the class of differential large fields, you only have to check for this prototype differential field. Okay? But this is not differentially large, I should point out. Right. By the way, also, you cannot reduce it to T1. That doesn't work. You cannot bring it down to T1. But now this also gives us some information about DCFs. So if I want to know in the theory of DCF, if I want to know, which differential equations are consistent, just consistent, right? In every differential field, then it turns out that the existential theory of DCF is just the existential theory of Q alge double bracket T. So I only have to check for solutions in this, Q alge T to check for consistency. Okay. And similarly, in the case of closed order differential fields, I only have to check in the real closure of Q double bracket T. Okay. Okay. Now, in parallel to the fact that algebraic extension of large fields are again large, well, it's a similar result for differential large fields. If I take an algebraic extension of differential large fields, it's again differentially large. Okay, and this gives us a nice kind of corollary that if I take any differentially large field and I take its algebraic closure with the unique derivation, right? I probably should have mentioned this before the theorem, that because I'm in characteristic 0, any derivation extends uniquely to any algebraic extension. Anyways, the algebraic closure of a differential large field is a DCF. And the real closure of an orderable differential large field is a CODF. Okay, and just a quick remark about this. In general, just want to remind you that differential fields, in general, they don't have minimal differential closures, right? They have differential closures. You know this, they always exist. But in general, there's no minimal differential closure, right? However, number 1 tells us that differentially large fields do. If any differentially large field has a minimal differential closure, which is just the algebraic closure. Okay, so it gives you lots of examples of differential fields with minimal differential closure. Okay, now I think I'm on time. PAC fields. Recall that a field is called a PAC field, pseudo-algebraically closed, if K is existentially closed as fields in every field extension in which K is algebraically closed. So, if K is algebraically closed inside L, then K is existentially closed in L at the level of fields. Okay, and then it's not hard to check that PAC implies large. Okay, this is all in the algebraic context. And now, what is the differential analog for PAC field? Okay, for differential fields, it's similar. That a differential field K delta is PAC differential if it is existentially closed as differential field in every differential field extension L delta in which K is algebraically closed in the field sense. Okay, in the field sense. So there's a question in the chat. Where the theories of large and differential large fields lies in the universe? I'm guessing by the universe, you mean the model theoretic universe? If that's the case, okay, perfect. Yeah, so I think I mentioned this, that if you take a differential large field, right, then basically it just depends on when the theory of the field lies in the universe. Okay, so for a differential large field, you only have to look at the underlying field. If the underlying field, it's stable, then differential large field will be stable. And if it's if it's MIP, it will be MIP. So things like that. Basically, it follows from the property that if the underlying field is model complete, then the differential one will be model complete. And so these properties like model completeness, quantified elimination, they transfer. Okay, basically to give you, tells you more or less where they lie. It basically only depends on the underlying field. Okay, I hope that answers the question. Okay. Right, going back to PAC-differential. So this is the definition, right? Whenever I have a differential extension in which K is algebraically closed in the field sense, then it is existentially closed in the differential field sense. And of course, you might wonder why in the field sense? Why like algebraically closed in the field sense and not differential sense? And this is because the AC, if you remember, the ACL in the sense of the theory DCF is just the field theoretic algebraic closure of K. The field theoretic algebraic closure of K. And that's the reason. That's the reason you only take the relative algebraic closure. Okay. Okay, so this is the definition of a PAC differential field. And this really, I mean, this is just specializing the definition of a PAC structure in the model theoretic sense. There's the definition of what a PAC structure is, and this is just specializing into the differential context. So something else in the chat. In general, there are around -1. The intuition is how complicated is absolutely directly. 5.1 is fine from stable. Okay, thank you for that post. Okay. Okay, right. Okay, and now I want to kind of make a connection between PAC fields, PAC differential and differential large. And it's given by this theorem. A differential field is PAC differential if and only if the underlying field is a PAC field and the differential field is differentially large. This is kind of a strong connection between these two notions. Okay. And a corollary of this theorem is that the class of PAC differential fields is first order. It's an elementary class. And this is important because in the general model theoretic case, when you talk about PAC structures, there are some theorems that say that if the class is first order, then this and this happens, just in the general context of PAC structures in model theory. Well, the fact that this case is actually first order allows you to apply these theorems. And I will talk a little bit about this at the end of the talk, which I'm almost there. Okay, so that's that. So I talk about differential large fields, and now I want to talk about this PAC differential just a bit more. And I think I just need like 10 more minutes just to finish more or less on time. Okay, so let's move on now. We talk about differential large fields. Now let's move on to PAC differential. And as I said at the beginning of the talk, I want to talk about ways of constructing these PAC differential fields. Okay, so now let's digress a little bit about model theory of groups acting on fields. The model theory of just groups acting on fields has been widely studied by several people. Just several names in there. I'm definitely missing names, but I tried to put as a complete list of names I could think of, but I apologize to people that are not there. Anyways, I've been widely studied. But the differential case, not so much. Namely, you have a group acting on a differential field by differential automorphisms. Okay? But some special cases have been considered. For instance, when the group G is the integers, then this just gives you the theory DCFA, studied by Bustamante. But more generally, when the group is the free group in M generators, then this has also been considered, and it's some work that Rahim and I did a few years ago. Okay, but okay, these are just special cases. What happens in general? Okay, so what is the setup? What's the general setup here? Okay, take an arbitrary group and consider symbols, sigma G's. So of course, sigma G's are going to represent, for each G in the group, I have this differential automorphism. That's what these symbols represent, differential automorphism, when you interpret them in a structure, right? And we work in the language of differential fields with these automorphisms. And this GDF is just a convenient way of denoting the theory of G differential fields. So differential fields equipped with a difference structure with the property that it's not just an arbitrary difference structure. It's one that when it goes from the group to the differential automorphism. So they're actually differential automorphisms, right? And this assignment is a group homomorphism. The assignment from G to these automorphisms of K is a group homomorphism. Okay, one can write this down in first order axioms. Okay. Okay, and so these are G differential fields. Okay. Now, these models of GDF are just substructures of models of DCF where they are substructures equipped with some action of G, right? And so this falls in a very general framework developed by Daniel, which I think is called something like model theoretic dynamics. Okay, it falls within this framework, and so we can apply some of his results. For instance, this one. Assume, this is an assumption here, assume that this GDF, this theory of G differential fields, has a model companion. Let's say it's called GDCF. If this happens, then the following are equivalent. The underlying field is bounded. Okay, the underlying field has a simple theory. The underlying differential field has a simple theory, and the whole differential difference field has a simple theory. Okay. Okay. But of course, the point is that notice that there's this assumption, right? And so the first question to ask is, well, when can you prove the existence of a model companion? And in general, for an arbitrary group G, it's a very difficult question, even in the case where you're working just with fields with group actions, right? Right. Okay. And in general, we know that it's not possible in general, but to find a model companion. But in some cases, we know it's true. And so what Daniel and I, this recent work that we did a few months ago, well, no, that's not true, more like a year ago, we explored the case when the group is finite, which was already done in the field case by Oslem and Piotr. We wanted to look at it in the differential case. Okay, so we proved it. We proved that if the group is finite, then this theory has a model companion. We wrote down axioms, and we proved that these axioms actually give the model companion. Okay, now I want to state some further model theoretic properties of this model companion. So from now on, assume G is finite, and assume it's non-trivial. Assume this group is non-trivial, because if the group is trivial, then you're back to DCF. If the group is trivial, you're back to DCF. So I'm going to assume from now on G is finite, and it's just not the identity. Okay, one piece of notation, which is pretty standard, is that if I have a G differential field, then this denotes the subfield of invariance under the difference structure. The things that are fixed by all the sigmas. Okay, and then one thing to note is that this field of invariance, together with delta, is a differential subfield of K delta. Okay. I think I have. Oh, sorry, Dave. I need like 3 more minutes, Dave. Is that okay?
Sure. Go ahead.
Okay, perfect. Yeah, I only have. I think I only have 2 slides left. Okay. So again, remember what are kind of further model theoretic properties that Daniel and I observed. Remember, I'm assuming now G is finite and non-trivial. Okay. Okay. Now take a model of this model companion, GDCF. Then, okay, first property. The field K, the underlying field K, and the field of invariance. Oh yeah, by the way, this this should be sigma. I just kind of changed notation from. Anyways, it's the field of invariance. They're both bounded as fields. They're both bounded fields, so they have finite extensions for each degree n. And also, they're not pseudo-finite, and they're also not algebraically closed. Okay. Okay. Next point is that at the differential level, at the differential field level, K delta and the invariance with delta, they are both PAC differential. These are examples of PAC differential. So this brings me back to what I said. This sort of model companion gives you a way to construct these PAC differential fields. So whenever you have one, the underlying differential structure is PAC differential for the whole field and for the invariance. Okay. So it's a question by Zoe. Let me address your question. Let me just finish the theorem and I will address your question. So just give me 1 sec. The next one is that you're right. If I take all of the structure in K, so K delta sigma, that's has a super simple theory. And if I take invariance with delta, that also has a super simple theory. And after adding a suitable tuple, okay, I'm going to really talk about much about this, but this is a natural thing to do. Add a suitable tuple that codes the fact that this is bounded, then you eliminate imaginaries as well. Fully eliminate imaginaries. Okay, now let me go to Zoe's question. It says, what if G is Z mod N? Why isn't it psi? Sorry, are you asking about which point? Point 1 or point 2?
I was asking why it isn't PSF when G is cyclic.
Oh, right. Why is it not pseudo-finite? Right, definitely.
As a field, of course, not as a differential field.
Yeah. This is as a field, yes, exactly. So why is it not pseudo-finite?
I would think it is.
I think this was a consequence of.
I mean, I would think that the Gara group is the whole Gara group is cyclic. It's a pseudo-finite field with an automorphism of order n.
But is the absolute Galois group going to be Z hat or only the primes that occur?
That's what I'm saying.
The absolute Galois group is Z hat.
I would have expected only the prime divisors of n to somehow feature in the absolute Galois group, but perhaps I'm totally out there.
Yeah, okay, I mean, right. Yes, right, you're right. It's not, okay, thanks.
Okay,
yes. So it's going to be, right, okay. Yeah, absolutely,
okay,
of course, right.
Okay.
Yes,
so yes, sorry, I usually with this example takes me a while
it's a product of copies of, I mean, it's a product of various cyclic groups, but it's not.
Okay, that's what it is. Okay, in that case,
okay, thank you.
Okay,
yeah.
No, well, I mean, I'm sorry, I didn't really give much input in this, but I'm happy that the question was answered. Okay, so yeah, it's not pseudo-finite. Okay, and okay, so the last slide is about, okay, we have these properties about, you take one of these models, and they have a super simple theory and all these things, but maybe there is more going on here. Maybe this is just something which is true about any arbitrary bounded PAC differential field. And this is the content of the last slide, okay? That is, yeah, it's the case that if you start with a theory of a bounded PAC differential field, and again, you add this suitable tuple that codes boundedness, and you consider the expanded theory, this delta should be little delta. You can imagine, okay. The theorem is that yes, if you take any such theory, then it's going to be model complete, super simple, and will eliminate imaginaries. And these are all differential counterparts of known results about bounded PAC fields, okay, by several people. And if you've ever seen these proofs, kind of one of the most natural ingredients is this last result, which using some general results by Daniel and Jungkook, you get that if I have differential field extension, both of them PAC differential, and the restriction map on the absolute Galois groups is an isomorphism of profinite groups, then actually it's an elementary containment, right? This extension of differential field is an elementary extension of differential fields. This is kind of one of the key ingredients for these things. Okay, and yes, that's it. That's really, I'm going to stop here. So thank you very much.